In 10.3, we're going to talk about the composition of functions. So we are still taking multiple functions and putting them together to create a new one. However, we are not going to put them together using a traditional operation like adding, subtracting, multiplying, and dividing. We are putting the functions together a bit different. A composite function is a function that is the result of two or more functions being applied successively. That is to say that the composite function is a function of a function. Recall that in a function, each input only has one output. In a composite function, the output value for one function becomes the input value for a different function. It's like taking a function and putting it inside the other one. So x is going to operate on the inside function. It gives a y value. That y value becomes the x value for the outside function. We have some different notation for this. The composition of f and g is defined as, now, f at g at x or f at g at x. So have a look at these. It is not multiplication. So we should maybe highlight that. It is not a multiplication question. So you'll notice that when we talked about multiplication, we wrote it much differently. And I'm going to write it up here so we don't get confused. It was either f close dot of g at x or f at x times g at x. And we didn't see it much, but sometimes you see it as fg at x. But you'll notice how f at x and g at x are either joined with a closed multiplication dot or with nothing in between. In composite functions, we have f bracket g at x, which doesn't mean f times g at x. You'll notice the x of f at x is gone, and in its place is g at x. Alternatively, we write it as f. Now, notice that this dot is open. That means something different than the closed dot of multiplication. It means composite. And again, it means we have taken the x out of f at x and replaced it with the function g at x. So g at x is substituted for x in the expression representing f at x. And that's worth highlighting too. The inside function is substituted for x into the outside function. Interesting to note as well, gf at g is different than g at f. The order matters. So the first one means that g at x is replacing x in f at x. The second one means f at x is replacing x in g at x. So our inside function would be different than our outside function, and the resulting function is going to be different. When we look at the domain of the composite functions, we are going to do two steps. So it's not just the common domain like it was with most of the operations. It's a little bit different. Our first step is to find the domain of the inside function g at x. So decide if there's any restrictions, keep them. If there is a domain there, there will be a domain there. But if there's restrictions, write them down, keep them. Then construct the actual composite and look at the composite itself. Determine the domain of the composite and then put your restrictions from the composite, if there are any, together with the restrictions from the inside function. That is your domain. So a little different, that we're not just going to look at the parent functions here and their domains. We're going to look at the domain of the inside and then the domain of the resulting function and see where the common domain is between those two. So a little different than with the operations. Let's go ahead and have a look at a couple of examples. Given that f at x is equal to the quadratic function 2x squared minus x plus 1, g at x is linear, x minus 5, h at x is radical, root x minus 3, write simplified expressions and state the domain for. Okay, here's our first one. H at g at x. Again, note that that dot in the middle is open, which means we're not talking about multiplication. We are talking about a composite. Another way of writing this would be h at g at x. What does that mean? That means we are taking this entire function of g at x and substituting it in for the x in h at x. So h, we can plug in the letters g at x, if that helps, is the square root of, instead of x minus 3, it's going to be g at x minus 3. But because g at x is x minus 5, let's replace the g at x with x minus 5. So we are literally taking that function of g at x and replacing the x in h at x. Removing the brackets and simplifying on the inside there, we get root of x minus 8, and there is our composite function. All right, let's talk about the domain. So the first thing we're going to do to decide the domain is we need to look at our domain of our inside function, the domain of g at x. And in this case, because g at x is linear, it's going to be the set of all x, such that x is an element of the reals. Second, we're going to look at the domain of the composite. So the domain of the new function that we just created, which is right here, that root x minus 8. It's a radical function, so it does have a restriction. And in this case, the domain of the composite function is a set of all x such that x must be greater than or equal to positive 8. Otherwise, x is the element of the real. So you can get that from the fact that our radicand has to be positive. You could also get it from the fact that this is the graph of root x that's been moved 8 units to the right. Either way, there is your domain. So now to find the domain, our final domain, it is where these two domains are common, which is going to be the last one. So in the end, our domain is the set of all x such that x is greater than or equal to 8. Otherwise, x is an element of the reals. So we take the domain that is common to the inside function and the composite. Let's try part B. Part B, again, that does not mean f times g at x. It means f at g at x. So this time we are taking our g at x and plugging it into f at x. So f at x has two x's in it, which means g at x is going to park itself right there and right there. So we can write it in general form. It would be 2 instead of x squared to g at x squared. Then instead of minus x, minus g at x, then plus 1. So we took the x out and replaced it with g at x. But we know the equation for g at x. It's x minus 5. So let's replace the x with x minus 5. 2 times g at x squared becomes 2 times x minus 5 squared minus g at x becomes minus x minus 5 plus 1. You'll notice we're very careful when we substitute to use brackets. Okay, next we need to expand. Now please be careful. X minus 5 all squared means x minus 5 times x minus 5. So we're going to distribute and collect like terms. That gives us x squared minus 10x plus 25. Also being aware when we remove the brackets here, that negative applies to both terms. So it's going to be minus x plus 5, and the plus 1 still hanging on to the end there. My last step is going to be to distribute the 2, and then we're going to be able to collect like terms. So we have 2x squared minus 20x plus 50 minus x plus 5 plus 1. And let's collect like terms. There's only one x squared, or one x squared term, so 2x squared stays. We have a negative 20x and a negative x, which gives us negative 21x. And then we have a 50 plus a 5 plus a 1 is positive 56. And there is our composite function. Let's decide on what the domain is there. So first of all, we're going to look at the domain of the inside function. So we're going to check out g at x. Its domain, again, it's linear. We already talked about it before. X is an element of the reals. Second, let's have a look at our composite function. Here's our composite function right here, and it is quadratic. So its domain is also the set of all x, such that x is an element of the reals. Well, common domain, pretty easy to see there. So in the end, our domain is the set of all x, such that x is an element of the reals. Pretty easy to see the common domain there since the domains are the same. Our last one. So a little more work with this one. This is a composite of 3 functions. So this is f at g at g at x. A little confusing. F at g at g at x. So we're going to take it a step at a time. We're going to work always from the inside out. So this is going to look different because g at x is acting on itself. So we are replacing the x with g at x in g at x. So g at x, instead of x minus 5, we're going to have g at x minus 5, but g at x is x minus 5. So we have x minus 5 minus 5, which is x minus 10. So g at x is x minus 10. And now that we've determined the inside function, now we're going to take that one and we're going to substitute it into f at x. We found g at x. Now we're going to evaluate f at g at x. So just like in the previous example, that means it's being substituted into both places where the x is. So f at g at x is going to be f at x minus 10. So 2 instead of x squared, x minus 10 squared, minus, instead of x minus 10, plus 1. Again, we're going to start with expanding. I'm going to keep the 2 there for now. This is x minus 10 times x minus 10. So x squared minus 20x plus 100. Removing the brackets is going to change the sign of both of those terms. So minus x plus 10 plus 1. Distributing that 2, we're going to get 2x squared minus 40x plus 200 minus x plus 10 plus 1. And let's go ahead and put that all together. 2x squared doesn't have any other common terms, so it's just going to stay as 2x squared. We have minus 40x and minus x, so minus 41x, and 200 plus 10 plus 1 will be 211. And there is our common, or our composite function. Let's go ahead and determine our domain. So in this case, again, same 3 steps. We're going to look at the domain of our inside function, which is still g at x. So the domain there, x is an element of the reals. The domain of our composite, and our composite ended up being quadratic again. So its domain is x such that x is an element of the reals. So that means our domain is going to be the set of all x, such that x is an element of the reals. And we're done. Okay, so 3 composite functions that we just found the equations of. Example 2, we're going to do this again a composite. Please really make note of the difference between what a composite question looks like and what a multiplication looks like. If this was multiplication, that would be a solid filled in dot. It is an open dot, so this is a composite, and it means F at G at X. That means we are replacing F at X, all the X's in F at X with G at X. So that 2 over X is going to get substituted there and there. So F at G at X, instead of 3X, 3 times G at X, and instead of X minus 1, G at X minus 1. The equation for G at X is 2 over X, so 3 times 2 over X in the numerator, and in the denominator, 2 over X minus 1. Okay, we want a simplified expression here. So in the numerator, we can clean this up. This would become 6 over X. In the denominator, in order to clean this up, what we need to do is we need to get a common denominator. That common denominator is going to be X. So our first term is going to remain the same, 2 over X, but 1 we are going to rewrite as X over X. So what we get then is 6 over X over 2 minus X over X. Now that we have a simplified compound fraction, we can take the numerator, change the division to multiplication, and then reciprocate our second fraction. So instead of dividing, we multiply, and we reciprocate the denominator. We can see that we've got common factors of X in the numerator and the denominator, which divide out, and we're left with 6 over 2 minus X. There is our composite function. Now let's state the domain. Let's do those same 3 steps again. Step 1 is going to be the domain of G at X, our inside function, and it is rational. You'll notice that we have a non-permissible value at 0. So the domain is the set of all X, such that X cannot equal 0. Otherwise, X is an element of the reals. In step 2, we're going to look at our composite function, the function we just found. Look at its denominator. Its denominator is 2 minus X, so it has a restriction at positive 2, because that was what makes our denominator 0 there. So it is X cannot equal 2. Otherwise, X is the element of the reals. So our final domain then for our composite is going to be the domain that is common to these, which is going to be the set of all X such that X cannot equal 0 and 2. Otherwise, X is an element of the reals. So there we see that the 2 restrictions end up coming together to create one domain. Example 3, use the following information below to answer the following question. So we have f at x, which we are given as a actual function, rational function. G at x is given as a table of values, and h at x is given as a function. So what we want to determine is the value of k at 1 for given each of the following. So k at x, we can see, is different composites of the functions. And what we want to do is evaluate at 1. So let's see what that means with the first one. K at 1 means that we are determining G at F at 1, or what we might want to write as G at F at 1. So what this means is 1 is the X value for F. We're going to get the Y value for F at 1. And that becomes the X value for G. So let's find what F at 1 is equal to. Plugging into the function, F at 1 is going to be 12 over 1 plus 3 minus 1, which is going to be 12 over 4 minus 1, which is going to be 3 minus 1, which equals 2. So since f at 1 is equal to 2, that's the y value for f at 1. That y value becomes the x value for g. So g at f at 1 becomes g at 2. And now we're going to go look at the table. G at 2 is equal to negative 1. And that would be our answer. K at 1 is equal to negative 1. So the positive 1 acts on the f. That gives us a y value of 2. The 2 then acts on the g, which gives us our y value of negative 1. Let's have a look at B. K at 1 is going to be f at h at g at 1, which means f at h at g at 1. So working from the outside, inside out. So we're going to start with g at 1. G at 1, right here from the table, is equal to 3. So now we are at f at h at 3. The y value for g becomes the x value for h. H at 3, let's look at the graph going straight up. H at 3 is 6. So now we are at f at 6. And f at 6, we're going to plug into the function there. So that is going to be 12 over 6 plus 3 minus 1, which is 12 over 9 minus 1. So 12 would be 4 over 3 minus 1, which gives us 1/3. So K at 1 would be 1/3. And then finally, we have a mix of composite and an operation there. So K at 1 means G at F at 1 plus H at 1. So G at F at 1. F at 1 we found back here, that's 2. So that's going to be G at 2 plus H at 1. Let's look at the graph. H at 1 is up here at 5. And G at 2, we found that already. G at 2 is negative 1. And negative 1 plus 5 is 4. So K at 1 for this one is equal to 4. So there are some examples with composite functions. Always keep in mind that we work from the inside out, that the inside function always becomes the input for the outside function, whether we are creating the functions or evaluating, and that we have 3 steps for our domain. Find the domain of the inside function, find the domain of the resulting function, and then where they are in common is your final domain. Go ahead and do some textbook work to get some practice, and then review for the chapter.